Yeah, I get it. A little corny at the end there, but, was what it was. All right, so here's what we got to fill in terms of vocabulary and key concepts. Perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. That means that that's where they meet. And so that's a perpendicular bisector right there. So it meets here, perpendicular, and then bisects this angle down here. Bisectors of the angles of a triangle are concurrent at a point equidistant from the side. That's what this one looks like here. So each side is exactly the same distance away, this being the center of the circle, and this is what's called an inscribed circle. The medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. That's this example over here. All of these are exactly 2/3 of the way away from each other. So D to J to DC is 2/3 of the way. C to J is the other 1/3 of the way. And you can use that to find the centroid of a triangle. Concurrent lines are going to be 3 or more lines that meet at one point. The point of concurrency is the point at which the concurrent lines intersect. So this point right here is the point of concurrency. They meet together. The circle, or rather a circle, is circumscribed about a polygon. That means around a polygon when the vertices of the polygon are on the circle. What that means is that this circle is going around the triangle and meeting at the vertices, at the corners, at the angles. So it goes all the way around. That's a circumscribed circle as opposed to an inscribed circle, which would be a circle that would be inside of that. You've already seen an example of that. There'll be more to come. A median of a triangle is a segment that has at its endpoints a vertex of the triangle and the midpoint of the opposite side. So you start here and you're going down to the exact middle point between these two vertices of this triangle, or opposite, go from the exact middle point up to there. A circle is inscribed in a polygon if the sides of the polygon are tangent to the circle. That's the official definition of it. Tangent means that a straight line touches exactly one point on the circle and goes off into infinity, or it just starts here and goes off into infinity the other direction. Obviously, this stops right here, but it can continue on forever and ever. That's a tangent line. Another way of thinking of it is this way, is it touches each side in exactly one place. The incenter of a triangle is the point of concurrency of the angle bisectors of the triangle. So that's what this is. Angle bisector of V, of U, of T, where it meets right here in the middle. That's what's called the incenter. And then the altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. So it has to be a right angle going directly up to one of the vertices. A little bit more about altitudes. They can be in 3 different places depending on the size of the triangle. So if it's an acute triangle, the altitude will be inside of the triangle. If it's a right triangle, it can be one of the legs on the side. If it's an obtuse triangle, the altitude will be outside. Point is, it has to be a right angle up to the vertice. The centroid is the point of intersection of the medians of the triangle, right in the middle of that. And here's an example of the centroid. I've already shown you one on the previous page. It's the medians, and where the median bisectors meet. And then the orthocenter of a triangle is the point of intersection of the lines containing the altitudes of all the triangles. So there's the orthocenter. Even though it's not marked as being a right angle, it is a right angle because it's being labeled as an altitude. So the orthocenter is this point here. Sometimes the orthocenter can actually be outside of the triangle, but that's another story. Moving on. How do we use this? What can we do? I'm going to talk about all of this business here in just a second. But first, I want you to understand what in the world it is that we're trying to do. We want to find the circumcenter. Circumcenter means the center of the circumscribed triangle. So we want to draw a circle all the way around the triangle and have it touch each one of the vertices. Now, how do you find the exact center of that circle? Well, here's an easy way to do it. What you want to do is find the median point of the 2 legs of the triangle. The longest side is going to be the hypotenuse. If it's not a right triangle, just find the longest side, because you know that the longest side, if it's going to have a triangle in the middle of it, the longest side has to be part of what's going on. It has to be the diameter of the circle. So what we've got here, we've got this line going all the way across. So what I did was I've got x right here and z right here. I'm taking a look there. Well, it's 4 between x and z, so I'm going to go 1, 2 to right there, and then draw a vertical line at that point. Do the same thing between x and y. So x and y, the difference right there is going to be 6, so I go 1, 2, 3, and I draw a line over that way. Where they intersect, that point, which in this case is 3, 4, that is in fact the center of the circle. Now here's how they did it using the coordinates. Essentially the same thing. So we have a point of 1, 1 and a point of 1, 7. That's x and y. Then they did the midpoint formula, dividing both by 2, and you find out that a line of y equals 4 will be your point. So 1, 4 is the midpoint of xy. Same thing with xz. Midpoint ends up being right here at 3, 1. So our point, 3, 4. Now, applying Theorem 5-7, we got some city planners who want to locate a fountain equidistant from 3 straight roads that enclose a park. So how can we find the exact center of this particular park? Well, the theorem states that the bisectors of angles of a triangle are concurrent at a point that is equidistant from the side. So we want it to have a fountain right in the middle of the park, not off to the side, not somewhere else. We want it to be exactly in the middle, so that if you're driving along Highway 101 or Mariposa Boulevard or Andover Road, you're going to get to see an equal chance to see this particularly great and wonderful fountain. So the city planner should find the point of concurrency of the angle bisectors of the triangle formed by the 3 roads and locate the fountain here. So let's do that. So there's 1 angle bisector, 2 angle bisectors, 3 angle bisectors, and there you go. We found the incenter of the circle. Did I say circle? I meant to say triangle. Anyway, finding the lengths of medians. M is the centroid of triangle WOR, and WM equals 16. We want to find WX. I don't know if you remember back from the very, very first page, we talked about how the centroid is the point of concurrency of the medians of a triangle, and the medians of a triangle are concurrent at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. So because M is the centroid, because you're making medians here of WOR, then WM is going to be 2/3 of WX. Here's WM, and WX goes all the way across. So if we take WM using theorem 5-8 and take 2/3 of WX, we can then figure out what's going on. So they tell us that WM is 16, so we substitute 16 for that. And so 16 is equal to 2/3 of WX. So we multiply each side by 3/2 and we find out that WX is 24. The other way of doing it is simply to multiply 16 times 3/2, and that would have gotten us the answer as well. We're going to have to come back to this particular problem in a little bit, by the way. It is now time for you to take a shot on your own. On page 100, do the quick check. When you're done, come on back. Who's ready for some answers? Find the center of the circle that you can circumscribe about the triangle with the vertices of 0, 0, -8, 0, and 0, 6. So here's our triangle, and we have to make our own little grid here. And so if we put our points at 0, 0, and then another point here at 0, 6, and another point at -8, 0, and using what we talked about a little bit before, in other words, halfway across here, is since this is 8, this is going to be 1, 2, 3, 4, and then this is 6, so 1, 2, 3, so our point is going to be at -4 and +3. Now, in example 1, explain why it's not necessary to find the third perpendicular bisector. It's because all the perpendicular bisectors of the sides of a triangle are already going to be concurrent. 2a. The towns of Adamsville, Brooksville, and Cartersville want to build a library that is equidistant from the 3 towns. Show on the diagram where they should build the library and then explain. So we don't have to do a lot of math here, but we're going to make a triangle of Adamsville, Cartersville, and Brooksville, and then find out where exactly to build the library would be the intersection point of the perpendicular bisectors of the segments. What theorem did you use? The perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. All right, and 3, using the diagram in example 3, find mx. So we need the diagram from example 3. Hopefully you realize it wasn't the same thing that's staring at you in the face. So check that Wm plus mx equals Wx. So we already know that the centroid of WOR, m is the centroid rather, and Wm equals 16. And then we figured out that Wx was 24, so pretty easy math here. 24 minus 16 going to give you 8. Finally, is my a median, an altitude, or neither? It is a median because an altitude would have to be a right angle. Well, here's a right angle. This right here is an altitude. This is a median right here. All right, our objectives today were to develop some methods for applying theorems about triangles to find and prove various things out about triangles. So we can find points of concurrency in triangles and find medians and altitudes in triangles as well.